Alright, today we're going to continue with decimals for fractions. This is the second video. We're going to talk about how to deal with what is called mixed recurring decimals or pure recurring decimals, and of course how that is related to the geometric sequence and sum of geometric sequence. Okay, let's get started. First of all, we study the fractions and decimals, and we can only limit the case where the leading integer value is 0. In other words, the fraction we assume m over n, where mn is coprime and also m is smaller. Okay, so for the case where there's integer part, we can just remove the integer. So the decimal part is always 0 dot something, for example. Okay, so that would equal 1/8, right? So for the case where if you have, let's say 10 over 8, we're not going to consider this case. Okay, now when we say a decimal number could be recurring, for example, one example is 0.4545 and go on forever, and we use notation 0.45 with parentheses. Now some other user would like to say 0.45 with like over bar on the top. Okay, but here we don't use that. The reason for that is sometimes we want to use symbols. For example, let's say digit 1, digit 2, I put a bar on top of it to represent the fact that I'm going to treat that digit as a number. For example, D1 could be 4 and 5. When I put it like that, it means I take that as 45 as an integer number. All right, there's some notation here. Okay, so now for the case where if the repeating part, okay, the recurring part, happens immediately after this decimal position, we call it pure recurring. Sometimes people say repeating. Decimals. And for the other case where you may not immediately start the recurring pattern, you may have something like 1, and then here you say 2, 3, 2, 3, 2, 3. That's repeating. So the notation here is going to be 0.1, but then for the part where 2, 3, that's repeating. So here there's some non-recurring position at the beginning, right? So in that case, we call it a mixed recurring, in contrast to the earlier say pure recurring, right? Decimals. Okay, the difference is that there's some extra term here, right? So we're going to study both cases and see how to convert those into a fraction. Yeah, so let's get started. Now we're going to take this as example, right? Now this repeating pattern can be, this is written as 0.45, 45, 45, and goes on forever, right? So one way to think about this is consider a geometric series, right? Geometric sequence, where the initial term is 0.45, and then the second term is going to be 0.0045. Yeah, every time you're going to divide by 100, 0.000045, and so on and so forth, right? So in this case, the geometric sequence here, the common ratio R would be 1 over 100. Okay, so what is x? X is considered the summation of this geometric sequence, right? So let's say if I call this term as a1, a2, a3, and so on and so forth, right? So x is nothing but a1 plus a2 plus a3 and goes on forever, right? That is the sum of I equal 1 to positive infinity a I. Now notice that the geometric sequence for the infinite sum, if the common ratio, the absolute value, is less than 1. In this case, indeed, the ratio is 0.01 is less than 1. Then you know that this thing converges. The zero sum converges. And there's a formula here. This is just to recall. In the geometric series, if the common ratio absolute value is strictly less than 1, then the infinite sum is going to be the first term, 1 minus the common ratio. Okay, so here is the first term. Okay, so first term is A, right? And R is, R, the common ratio, right? So in this case, we just plug in the formula here, right? Let's do that. So here, the first one is 0, 4, 5, and 1 minus R, 1 minus 100, 1 over 100. And multiply 100, then on both top and bottom, what you get is 45 over 99. Okay, so that is one way of considering the what is called pure recurrent decimal. The value is actually equal to the sum of infinite geometric sequence, right? Now for that, typically there's another interpretation of it, right? For the value here, if you increase by 100 times, and then you're gonna shift the decimal here, 2 position, become 45 integer part, plus the fraction part is gonna be the same thing repeating, that is x. So what is the intuition for this equation here? What we're saying is that if we increase the value by 100 times, the value increase 45. So which means 45 represents 99 of the original value. So that is 45 is 99x, right? This is both from the algebra itself or from such intuition, right? So in that case, we also get the same conclusion here, 99. Now similarly, you're going to have, in general, let's say for another example, right? Whenever you have a repeating pattern here, then it's just this particular value treated as an integer and then divided that by the same number of 99 here, right? So another example here, if x equal 0, 1 to 8, yeah, then we know that use the same reasoning either using the geometric sequence or this algebra or intuition. What you get is 1 to 8. This is 3 digits, so I have 3 nines. Okay. Of course, sometimes if there's a common factor, in this case, in the first case, you can divide by 9. So that is actually 5 over 11. And in this case, they're already ready to prime here, so just keep it as this fraction. Okay, so that's for the case of what is called pure recurrent decimals. Now the other case, that is mixed recurring decimals. So if you have a term that is non-recurring, and this is a recurring part, right? So what we can do is to split into two parts, right? So this is equal the first part, which is just 0 to 0, plus the second part is 0 to 0, 0, and then 128, right? Earlier, we know that from the previous analysis, we know that if this 0.128 repeating is going to be 128 over 999. Now, in this case, you divide it by 100, right? So the second part, what you're going to do is it's going to be 128. Instead of 999, you're going to add two zeros to the end, right? Representing this part, because the positions, there's two extra positions here. And this part, of course, is just 100 over 20 over 100, right? Plus. Now, you need to combine these two fractions. It's going to be 99900, okay? So this part, you have to multiply 999 on the top, right? So instead of 999, we're going to write 1000 minus 1, right? So you're going to times 20 times 1000 minus 1 plus 128. Why do I need to write that? So here I want to combine this term and 128. What you get is 20128. And then you need a minus 1, right? Minus 20 and over 99900. Okay, so that is 20108 over 99900, and that can be reduced because there's a common factor of 4 here, I believe. So what you have is, let's see, 5027 over 9900 divided by 4. That's about 24975. Okay. Now the key here is this part, right? So why I write like this? Now notice that what is 20128? That is, you treat the whole thing as an integer, right? The non-recurring part and take one part of the recurring. Okay, combine this as an integer here, and then you minus 20 divided by how many digits you have, and how many nines you have, and how many zeros you have. It depends on the position here, right? So in general, there are two cases, yeah. So the two cases, one is for the pure recurring. Let's say 0 dot, let's say digit D1, D2, and DK, K digit. What we're gonna have is, we're gonna have a bunch of nines on the bottom. How many of them? There's K of them. And we're gonna use this number here, D1, D2, the digit together as a number, right? On the top, okay? And again, this bar notation meaning I treat the whole thing as an integer value, right? Divided by, okay? Now the other case where it's mixed. So for the mixed, you're gonna have what? 0 dot, there's some digit that's non-recurring. Let's say T1 transient, T2, and T, let's say S, right? And then you have repeating one, D1, and then up to DK, yeah? So what you do here is gonna be 999, you have K of them, and then 000, you have S of them, okay? And then here, you treat the whole thing as an integer, T1, T2, and TS, D1 and DK, all the digit as an integer, minus this part here, the first part here. So minus just the non-recurring part as an integer value, T1 and TS. Okay, so I give another example just to be specific, right? So for example, if I have 0.14 and then 45 repeating, then in this case I'm going to write it as 99. Why I have 99? Because 45 two digits, and then this two digits I'm going to put 0, 0, yeah, and here because this part meaning I'm going to combine the whole thing as an integer value. That's going to be 1445, and then after minus the part that's the first part, non-recurring part, that would be 14. Okay, so that is 1431 over 9900. Of course, you can further reduce because this is multiple of 9. Yeah, so I'm going to skip that. But today we just covered, mainly two different cases, and then how to convert that into a fraction value. Now, what we're going to do is, now notice that in some cases, let's say 1 over n, the actual value could be terminating, could be terminating, that is recurring, and then we're going to study what is the period length in the next video. Right? Please like, share, and subscribe to the channel